The combat intelligence dossier slammed across the polished mahogany desk of Captain Akira Hayashi at the Kansai Regional Air Defense Headquarters on October 8, 1943, carrying battlefield analysis that would shatter every tactical assumption Japanese aviation commanders held about American heavy bomber defensibility. The classified document, painstakingly assembled through recovered gun camera film, pilot survivor testimonies, and wreckage examination from downed B-17 flying fortresses, documented that each Boeing aircraft mounted 13 synchronized defensive machine guns, delivering more concentrated air-to-air firepower than 3 complete squadrons of Mitsubishi A6M Zero fighters could bring to bear during coordinated attack formations. Captain Hayashi, the brilliant tactical analyst who had orchestrated Japan's early interception victories over the Doolittle Raiders and subsequent Allied reconnaissance missions, stared at defensive specifications that fundamentally challenged everything Japanese aviation doctrine had established about heavy bomber vulnerability patterns. His reputation had been built on mathematical precision in calculating attack vectors, ammunition expenditure rates, and pilot survival probabilities that had given Japanese fighter squadrons devastating advantages over Allied aircraft throughout the Pacific Theater's opening campaigns. The Kansai Command Center had received weeks of increasingly contradictory field reports from squadron leaders operating out of Matsuyama, Kanoya, and Omura air bases, where veteran pilots were filing combat assessments that defied logical explanation. Flight commanders reported successful approaches against American B-17 formations only to encounter defensive fire patterns that seemed impossible given the aircraft's size, weight, and presumed focus on bomb delivery rather than air-to-air combat capability. Colonel Watanabe's 54th Fighter Regiment had initially celebrated their first encounters with American heavy bombers, assuming these lumbering giants would provide easy targets for experienced Zero pilots who had honed their skills against nimble Allied fighters throughout the Solomon Islands campaigns. The preliminary engagement reports from September 1943 described B-17's as sluggish, predictable aircraft that maintained steady bombing approaches while Japanese fighters exploited superior maneuverability to attack from optimal angles with minimal defensive resistance. Squadron intelligence officers at Hiroshima Air Command had confidently briefed pilots on American bomber characteristics based on pre-war assessments and early combat observations that suggested heavy aircraft prioritized payload capacity over defensive armament. Japanese tactical doctrine had been developed around the assumption that strategic bombers represented vulnerable targets during the critical minutes of bombing runs, when crews would be focused on navigation accuracy, target identification, and bomb release timing rather than maintaining defensive vigilance against attacking fighters. The morning briefing sessions conducted by Major Ishida at the Nagoya Fighter Training School had consistently emphasized the tactical advantages Japanese pilots possessed against heavy bombers: superior climb rates, tighter turning radii, higher service ceilings, and concentrated forward-firing armament that could deliver devastating attacks during brief engagement windows when American aircraft would be unable to respond effectively due to their size, weight, and operational priorities. But the intelligence reports accumulating throughout late September and early October 1943 painted a dramatically different picture of American bomber capabilities that challenged every fundamental assumption Japanese tactical planning had incorporated into fighter doctrine, pilot training curricula, and strategic operational planning for intercepting Allied bombing campaigns targeting Japanese industrial centers and military installations. The shocking reality. The classified intelligence analysis revealed systematic defensive capabilities that transformed American heavy bombers from vulnerable cargo aircraft into flying battleships engineered for sustained aerial combat operations. Each Boeing B-17G Flying Fortress carried 13 Browning M2 50 caliber heavy machine guns strategically positioned in overlapping defensive positions that created interlocking fields of fire covering every conceivable approach angle. Japanese Mitsubishi A6M Zero fighters, by stark comparison, mounted only 2 Type 99 20mm cannons and 2 Type 97 7.7mm machine guns, representing less than 1/6 the total defensive firepower that individual American bomber crews wielded against attacking interceptor aircraft. The tactical ramifications were mathematically staggering. While Japanese fighter pilots approached bomber formations expecting brief vulnerability windows during high-speed attack runs, B-17 crews maintained continuous defensive fire from multiple synchronized gun positions that eliminated safe approach corridors Japanese tactics had assumed would exist throughout engagement sequences. The nose-mounted chin turret, Sperry ball turret system, tail gunner compartment, flexible waist gun installations, and dorsal turret position created a defensive umbrella that provided 360-degree coverage against attacking aircraft, regardless of approach vector, altitude differential, or relative speed advantages. Lieutenant Colonel Tanaka's detailed analysis of combat film recovered from downed Zero fighters revealed defensive coordination that exceeded Japanese expectations of American crew training and tactical sophistication. B-17 gunners operated their positions with mechanical precision that maintained effective fire throughout complex aerial maneuvers, altitude changes, and evasive actions that Japanese pilots employed to break defensive tracking. The synchronization between multiple gun positions indicated systematic training programs that had prepared American crews for sustained defensive operations against coordinated fighter attacks. The Browning M2 .50 caliber machine guns mounted in B-17 defensive positions delivered ballistic performance that exceeded Japanese aviation armament specifications across multiple critical parameters. The heavy machine gun cartridge possessed superior range, penetration capability, and destructive effect compared to the 7.7mm ammunition used in Japanese fighter aircraft, while maintaining rate-of-fire characteristics that enabled continuous suppressive fire throughout extended engagement periods that Japanese ammunition had never achieved during operational testing protocols. The defensive ammunition capacity carried by individual B-17 aircraft represented logistical capabilities that Japanese aviation units had never possessed during extended combat operations. Standard ammunition loads exceeded 4,500 rounds of .50 caliber defensive ammunition distributed across 13 gun positions, providing sustained fire capability that could maintain effective defensive operations throughout multiple engagement cycles with attacking fighter formations. Captain Hayashi's preliminary calculations revealed that a standard 12-aircraft B-17 formation carried more total air-to-air firepower than 5 complete squadrons of Japanese fighter aircraft possessed for aerial combat operations. The mathematical disparity eliminated theoretical Japanese numerical advantages through superior American firepower concentration that could be brought to bear against attacking interceptor aircraft from multiple simultaneous defensive positions. Escalating evidence: the defensive gun system analysis. Systematic examination of recovered B-17 wreckage and captured technical documentation revealed defensive installations that Japanese aviation engineers had never encountered in previous combat aircraft analysis. The Boeing engineering team had designed each defensive position to maximize coverage while minimizing vulnerability to counterattack, creating a defensive philosophy that prioritized crew survival and mission completion over weight reduction or manufacturing simplicity that Japanese aircraft design had emphasized throughout military aviation development. The chin turret installation, designated as the Bendix Model A5, mounted twin Browning M2 machine guns in a power-operated turret that provided comprehensive forward hemisphere coverage against head-on attacks. Japanese fighter tactics had consistently exploited frontal approach vectors against heavy bombers, assuming minimal defensive capability in forward-firing positions due to aircraft design constraints and crew positioning limitations. The chin turret eliminated this tactical advantage through mechanical gun-laying systems that tracked attacking aircraft with precision that human gunners operating flexible mounts had never achieved in Japanese combat experience. Technical specifications recovered from crashed B-17G aircraft documented turret traverse rates of 35 degrees per second in both azimuth and elevation, enabling rapid target acquisition and tracking throughout high-speed engagement sequences. Japanese Zero fighters approaching at combat speeds of 350 miles per hour discovered that the chin turret maintained accurate tracking throughout approach phases, engagement periods, and breakaway maneuvers that Japanese pilots had assumed would exceed human reaction time and mechanical response capabilities. The Sperry A-13 ball turret system, suspended beneath the aircraft fuselage in a retractable spherical housing, represented mechanical engineering sophistication that Japanese aviation industry had never attempted in defensive armament installations. The turret provided complete 360-degree azimuth coverage with elevation ranges from directly overhead to straight down, eliminating the traditional vulnerability zone beneath heavy bombers that Japanese attack doctrine had exploited throughout previous combat operations against Allied aircraft. Inside the spherical turret housing, the gunner operated twin Browning M2 machine guns through mechanical controls that enabled precise tracking of attacking fighters throughout complex three-dimensional maneuvers. The ball turret's gyroscopic stabilization system maintained accurate fire even during aggressive bomber evasive actions, turbulence encounters, and formation position changes that Japanese pilots had assumed would exceed human reaction time and mechanical response capabilities.
British intelligence analysis revealed that ball turret gunners could maintain effective fire against targets at ranges up to 1,000 yards, significantly exceeding the engagement distances that Japanese fighter pilots had assumed would provide safety margins during attack approaches. The extended range capability meant that Zero fighters came under accurate defensive fire much earlier in attack sequences, reducing the time available for target acquisition, gun aiming, and effective weapons delivery that Japanese training programs had calculated for bomber interception missions. The tail gunner position, protected by armor plating and equipped with twin 50-caliber machine guns, covered the traditional vulnerability zone behind heavy bombers that Japanese pursuit tactics had exploited since the beginning of aerial warfare. American tail gunners operated from enclosed compartments that provided protection against defensive fire while maintaining clear fields of fire toward pursuing aircraft throughout extended engagement periods. Ammunition feed systems supporting the tailgun position enabled continuous fire without manual reloading interruptions that had characterized defensive installations in previous bomber designs. The twin machine guns could deliver sustained fire for over 3 minutes at maximum cyclic rate, providing defensive capability that exceeded the duration of typical Japanese attack sequences against heavy bomber formations. Flexible waist gun positions mounted on both sides of the B-17 fuselage created crossing fire patterns that eliminated lateral approach opportunities Japanese tactics had consistently employed against large aircraft formations. The port and starboard waist gunners operated 50-caliber machine guns from positions that provided comprehensive coverage of beam attack vectors while maintaining overlapping fire zones that attacking fighters could not avoid during side approaches. The waist gun installations featured quick-change barrel systems that enabled sustained fire operations without weapon overheating that Japanese aviation armament had consistently experienced during extended combat sequences. American waist gunners could maintain effective defensive fire throughout prolonged engagements, while Japanese fighter pilots discovered that their attack windows were eliminated by continuous accurate fire from multiple defensive positions. The mathematical reality of firepower disparity. Combat engagement statistics compiled through detailed analysis of squadron after-action reports painted a devastating mathematical picture of defensive effectiveness that rendered traditional Japanese fighter tactics operationally unsustainable against American heavy bomber formations. The numerical disparities were so overwhelming that individual pilot skill, tactical innovation, and strategic planning could not compensate for the systematic advantages that Boeing's defensive design philosophy had created through industrial engineering rather than military doctrine. Captain Hayashi's statistical analysis revealed that Japanese fighter squadrons were experiencing pilot loss rates of 23% per engagement with B-17 formations, while achieving bomber destruction rates of only 3.7% per mission. The mathematical relationship between Japanese casualties and mission effectiveness indicated that continued bomber interception operations would eliminate experienced pilot cadres within 6 months of sustained combat operations, while inflicting minimal disruption to American strategic bombing campaigns targeting Japanese industrial and military installations. Individual engagement calculations demonstrated that each B-17G Flying Fortress possessed more total air-to-air firepower than 12 Mitsubishi A6M Zero fighters combined. A standard 18-aircraft bomber formation carried 234 defensive machine guns capable of delivering coordinated fire against attacking interceptor aircraft from multiple simultaneous positions. The defensive firepower concentration exceeded the total armament of 4 complete Japanese fighter squadrons operating at maximum strength levels. The cyclic rate of fire achieved by B-17 defensive positions enabled each bomber to deliver approximately 15,600 rounds per minute of .50 caliber ammunition against attacking aircraft. Japanese Zero fighters, by comparison, could deliver maximum sustained fire rates of 600 rounds per minute from their combined 20mm and 7.7mm armament systems. The mathematical disparity meant that individual American bombers possessed 26 times the sustained firepower capability of attacking Japanese fighter aircraft. Ammunition expenditure analysis revealed that B-17 formations could maintain maximum defensive fire for over 8 minutes of continuous combat operations, while Japanese fighter aircraft exhausted their ammunition supplies within 2 minutes of sustained engagement. The logistical advantage enabled American bomber crews to outlast Japanese attack sequences while maintaining effective defensive fire throughout extended combat periods that Japanese tactical planning had never anticipated. Range and ballistic performance comparisons documented systematic advantages in American defensive armament that exceeded Japanese fighter weapons across multiple critical parameters. The .50 caliber Browning M2 machine gun maintained effective range of 1,200 yards against aircraft targets, while Japanese 7.7mm armament achieved maximum effective range of 400 yards under optimal conditions. The range disparity meant that American defensive positions could engage attacking fighters at distances that Japanese pilot training had assumed would provide safety margins during approach phases.
British penetration characteristics of American .50 caliber ammunition demonstrated destructive capability that exceeded Japanese fighter aircraft structural protection throughout critical airframe components. Single hits from B-17 defensive positions could disable Japanese aircraft systems, while Zero fighters required multiple accurate hits with 20mm ammunition to achieve equivalent damage against American bomber structures that incorporated armor protection and redundant systems. The mathematical analysis revealed that Japanese fighter pilots needed to achieve hit probabilities of 87% with 20mm ammunition to disable individual B-17 aircraft, while American defensive gunners required only 12% hit probability with .50 caliber ammunition to destroy attacking Zero fighters. The accuracy requirements created tactical situations where Japanese pilots needed to maintain precise gun laying under combat stress conditions, while being subjected to defensive fire from multiple positions, while American gunners could achieve mission success through volume fire techniques that Japanese training programs had never addressed. Formation-level calculations demonstrated that coordinated defensive fire from B-17 groups created kill zones that extended beyond visual range of the bomber formation. Japanese fighter pilots discovered that approaching within effective attack range meant entering defensive fire patterns that achieved lethal hit probabilities before Japanese weapons could engage bomber targets. The standoff distance required to avoid defensive fire exceeded the effective range of Japanese fighter armament, creating tactical situations where interception missions became mathematically impossible to execute successfully. Psychological impact on Japanese fighter pilots. Squadron debriefing sessions conducted at Matsuyama and Kanoa air bases began revealing pilot testimonies that fundamentally contradicted official intelligence assessments of American bomber vulnerability and defensive capability. Veteran aviators with extensive combat experience throughout the Pacific Theater described approaching B-17 formations as flying into a constellation of tracer fire that created impenetrable defensive barriers around American aircraft formations that eliminated traditional attack opportunities Japanese tactics had exploited against previous Allied aircraft types. Flight Lieutenant Kazuo Yamada of the 333rd Fighter Squadron filed detailed combat reports describing his first engagement with B-17G aircraft over Rabaul on October 3, 1943. His testimony documented defensive fire patterns that began engaging his Zero fighter at distances exceeding 800 yards, maintaining accurate tracking throughout his attack approach, engagement period, and withdrawal maneuver. The continuous defensive fire created psychological pressure that affected his gun-laying accuracy and target acquisition timing during the critical seconds when Japanese pilots needed to deliver concentrated fire against bomber targets. The psychological effect of sustained defensive fire was creating systematic degradation in Japanese pilot performance that training programs had never addressed through combat preparation curricula. Rookie pilots were demonstrating measurable hesitation during attack runs when subjected to defensive fire from multiple B-17 gun positions, while veteran aviators reported difficulty maintaining concentration during weapons delivery sequences when under continuous fire from .50 caliber machine guns that outranged Japanese fighter armament. Squadron leader Hiroshi Nishida documented psychological transformation among experienced pilots who had achieved multiple victories against Allied fighters, but struggled to maintain aggressive attack postures when engaging B-17 formations. The systematic nature of American defensive fire was creating anticipatory stress responses that affected pilot decision-making before actual combat engagement commenced, reducing the tactical effectiveness of Japanese interception missions through psychological factors rather than physical damage to aircraft or air crew. Medical officers at Japanese fighter bases began reporting increased incidents of combat fatigue among pilots assigned to bomber interception missions, with symptoms including tremors, sleep disruption, and concentration difficulties that had not appeared during fighter-versus-fighter combat operations. The psychological strain of attacking heavily defended bomber formations was creating personnel problems that Japanese military medicine had never addressed through previous combat theater experience. The continuous defensive fire maintained by B-17 formations created acoustic and visual effects that overwhelmed Japanese pilot sensory processing during critical phases of attack sequences. Pilots reported difficulty maintaining spatial orientation when surrounded by tracer fire from multiple defensive positions, while the sound of defensive fire interfered with engine monitoring and radio communication that Japanese pilots required for effective tactical coordination during complex interception missions. Formation leaders discovered that coordinating multiple Zero fighters against B-17 groups required new tactical approaches that Japanese training programs had never developed. The defensive fire from American bombers disrupted traditional Japanese formation flying techniques, forcing individual pilots to break tactical discipline to avoid defensive fire, which eliminated the coordinated attack sequences that Japanese doctrine had emphasized throughout fighter pilot development programs.
British. The psychological adaptation required for effective operations against heavily defended bombers demanded training modifications that Japanese aviation schools were unprepared to implement. Traditional emphasis on individual aerial combat skills proved inadequate for pilots who needed to maintain aggressive attack postures while being subjected to defensive fire from multiple positions that outranged and outgunned Japanese fighter armament systems throughout engagement sequences. Technical superiority analysis of American defensive systems. Engineering examination of recovered B-17 components and captured technical documentation revealed manufacturing sophistication that exceeded Japanese aviation industry capabilities across multiple critical design and production parameters. The Boeing engineering team had incorporated advanced metallurgy, precision machining, and quality control systems that enabled reliable operation of complex defensive installations under combat stress conditions that Japanese military equipment had never achieved during operational testing protocols. The Browning M2.50 caliber machine gun mechanism demonstrated mechanical engineering excellence that surpassed Japanese aviation armament specifications in reliability, durability, and performance consistency. Individual weapons functioned effectively after firing thousands of rounds under combat conditions, while comparable Japanese aircraft armament experienced frequent malfunctions that compromised pilot effectiveness during critical engagement periods. The American manufacturing philosophy emphasized systematic quality control that produced consistent performance across thousands of individual weapons components, while Japanese production methods relied on individual inspection procedures that could not maintain quality standards during large-scale manufacturing operations required for global military campaigns. Metallurgical analysis of recovered .50 caliber ammunition revealed alloy compositions and manufacturing processes that Japanese industry had never achieved in military cartridge production. American ammunition demonstrated consistent propellant burn rates, uniform projectile ballistics, and reliable ignition systems that functioned effectively under temperature variations, humidity changes, and storage conditions that had consistently caused performance degradation in Japanese ammunition supplies throughout extended combat operations. The synchronization systems that coordinated multiple defensive positions aboard individual B-17 aircraft represented electrical engineering sophistication that Japanese aviation technology had not approached in defensive armament integration. American bombers employed centralized fire control systems that enabled gunners to coordinate defensive fire patterns, share target information, and maintain overlapping coverage without interfering with adjacent gun positions through systematic communication protocols that Japanese multi-crew aircraft had never implemented. Quality control procedures supporting American defensive armament production indicated manufacturing standards that exceeded Japanese military specifications while achieving production volumes that Japanese industry had never attempted in aviation equipment manufacturing.
Statistical sampling techniques ensured consistent performance across hundreds of thousands of individual weapons components, while Japanese production methods relied on individual inspection procedures that could not maintain quality standards during large-scale manufacturing operations required for global military campaigns. The interchangeable component design philosophy incorporated throughout B-17 defensive systems enabled rapid maintenance, efficient logistics support, and standardized training programs that Japanese military organization had never achieved in complex equipment operations. American gunners could perform weapon maintenance, ammunition handling, and system troubleshooting through standardized procedures that functioned effectively regardless of individual experience levels or specialized technical training that Japanese methods had required for equivalent operational capability. Research and development programs supporting American defensive armament continued advancing weapon performance, ammunition effectiveness, and system integration throughout active production periods, contradicting Japanese assumptions about the relationship between quantity manufacturing and technological innovation. American engineers achieved systematic improvements in defensive capability while maintaining production schedules that Japanese research and development had never attempted during wartime equipment development cycles. The workforce diversity that contributed to American defensive armament production challenged Japanese understanding of industrial organization and technical capability requirements. Intelligence reports documented women, minorities, and immigrant workers performing complex manufacturing operations with competence that Japanese military tradition had reserved for male specialists trained through lengthy apprenticeship programs emphasizing individual expertise over systematic instruction methods that democratic industrial organization had proven more effective for large-scale technical achievement. The growing realization. Major Yamamoto's preliminary assessment reached Imperial Air Defense Headquarters carrying statistical documentation that challenged fundamental assumptions about American bomber operations. The evidence suggested that Boeing had designed B-17's as aerial combat platforms rather than vulnerable transport aircraft, creating systematic defensive advantages that Japanese interception tactics had never addressed through traditional fighter doctrine.
The implications extended beyond individual aircraft capabilities to encompass formation tactics that multiplied defensive effectiveness through coordinated fire patterns. American bomber formations operated as integrated defensive systems, where individual aircraft supported collective protection through overlapping gun coverage that eliminated attack opportunities that Japanese tactics had assumed would exist. Personal transformation among Japanese air defense planners began as they realized their tactical expertise was being applied against defensive systems that made traditional fighter advantages statistically insignificant compared to systematic American firepower superiority achieved through industrial design philosophy rather than pilot skill development. The documented proof revealed American engineering philosophy that treated bombers as survivable combat platforms rather than expendable delivery systems requiring fighter escort protection throughout operational missions. The comprehensive technical analysis that emerged throughout November 1943 revealed that American B-17G Flying Fortress defensive capabilities represented a revolutionary approach to heavy bomber design philosophy that had fundamentally transformed strategic bombing from vulnerable cargo missions into sustainable aerial combat operations. Captain Hayashi's expanded investigation, now supported by intelligence teams from Yokosuka Naval Air Technical Arsenal and Mitsubishi Heavy Industries, documented defensive integration that exceeded Japanese comprehension of multi-crew aircraft combat effectiveness. The Bendix chin turret installation, previously understood as a simple forward-firing defensive position, proved to be a sophisticated electromechanical system that incorporated advanced fire control computers, hydraulic power systems, and optical sighting equipment that surpassed Japanese fighter aircraft armament in technical sophistication.
The turret's Sperry K4 gun sight utilized gyroscopic stabilization and ballistic computers that automatically calculated lead angles, range compensation, and trajectory corrections that enabled accurate fire against maneuvering targets throughout three-dimensional combat sequences. Intelligence analysis revealed that Chin turret gunners achieved hit probabilities of 34% against fighter-sized targets at ranges exceeding 600 yards, compared to Japanese fighter pilot accuracy rates of 12% with forward-firing armament under equivalent combat conditions. The American fire control system eliminated human calculation errors that had consistently reduced Japanese pilot effectiveness during high-stress engagement periods, while enabling sustained accurate fire from bomber crews who had received standardized training rather than the years of individual instruction that Japanese pilot development had required. The Sperry ball turret system, suspended beneath the B-17 fuselage, incorporated mechanical engineering innovations that Japanese aviation industry had never attempted in defensive armament installations. The spherical housing contained a complete fire control station where a single gunner operated twin .50 caliber machine guns through hydraulic controls that provided power assistance for rapid target tracking throughout 360-degree azimuth and 90-degree elevation coverage that eliminated traditional bomber vulnerability zones. Technical documentation captured from B-17 maintenance manuals revealed that ball turret operations included automatic ammunition feeding systems, spent cartridge disposal mechanisms, and optical sighting equipment that functioned effectively during complex aircraft maneuvers that had previously disrupted defensive fire coordination in multi-crew aircraft. The gunner's position included oxygen supply, heating systems, and communication equipment that enabled sustained operations at altitudes exceeding 25,000 feet during bombing missions that lasted 8 to 10 hours without degradation in defensive capability. The tail gunner installation, protected by armor plating exceeding 8 mm thickness, housed twin Browning M2 machine guns in a defensive position that covered the traditional pursuit approach that Japanese fighter tactics had exploited throughout previous bomber interception missions. The tail gunner operated from an enclosed compartment that provided protection against defensive fire while maintaining clear fields of observation and weapons engagement toward approaching fighter aircraft throughout extended combat sequences. Ammunition storage supporting the tail gun position included 500 rounds per gun, enabling continuous defensive fire for over 4 minutes at maximum cyclic rate without manual reloading procedures that had characterized defensive installations in Japanese bomber aircraft. The automatic ammunition feeding systems eliminated loading interruptions that Japanese pilots had exploited during tail chase attacks against Allied aircraft throughout Pacific Theater combat operations. Flexible waist gun positions mounted on both sides of the B-17 fuselage created interlocking fire patterns that covered beam approaches from port and starboard directions simultaneously. The waist gunners operated .50 caliber machine guns from stations that provided comprehensive lateral coverage while maintaining overlapping fire zones that eliminated safe passage corridors for attacking fighters attempting side approaches against bomber formations.
British waist gun installations featured quick-change barrel systems that enabled sustained fire operations without weapon overheating that had consistently limited Japanese aircraft armament during extended combat engagement periods. American waist gunners could maintain effective defensive fire throughout prolonged battle sequences, while Japanese fighter pilots discovered that their traditional beam attack tactics were eliminated by continuous accurate fire from multiple defensive positions that outranged Japanese fighter armament by factors exceeding 3 to 1. The dorsal turret position, mounted above the aircraft fuselage behind the cockpit area, provided upper hemisphere coverage through a power-operated installation that tracked attacking fighters throughout diving attacks, climbing intercepts, and high-altitude approaches that Japanese tactics had employed to exploit assumed blind spots in American bomber defensive coverage. The turret gunner operated twin .50 caliber machine guns through mechanical controls that enabled precise tracking of high-speed targets throughout complex aerial maneuvers. Broader context, strategic and industrial implications.
The systematic analysis of B-17 defensive capabilities revealed broader American advantages in aircraft design philosophy, manufacturing organization, and military doctrine that extended beyond individual weapons systems to encompass comprehensive approaches to strategic bombing operations that Japanese military planning had never encountered in previous warfare experience. The defensive integration demonstrated that American aviation industry had solved fundamental problems in multi-crew aircraft combat effectiveness through systematic engineering rather than tactical adaptation that Japanese methods had emphasized during previous warfare experience. Industrial analysis revealed that American aircraft manufacturing had achieved defensive armament integration without compromising bomber performance characteristics that Japanese design philosophy had assumed would be sacrificed for heavy defensive installations. B-17G aircraft maintained payload capacity, operational range, service ceiling, and cruise speed specifications while carrying defensive armament that weighed over 2,500 pounds, including guns, ammunition, armor protection, and fire control systems that Japanese bomber designs had never incorporated. The manufacturing coordination required to produce B-17 defensive systems indicated American industrial capabilities that exceeded Japanese total aircraft production capacity across all manufacturers and all aircraft types. Boeing factories had achieved systematic integration of components manufactured by dozens of specialized suppliers, including Browning machine guns, Sperry turret systems, Bendix fire control equipment, and thousands of precision parts that required coordinated delivery schedules and quality control standards that Japanese industry had never achieved during peacetime operations. Workforce development programs that enabled American defensive armament production included systematic training, technical education, and skill development that created industrial capabilities through democratic participation rather than hierarchical control that Japanese manufacturing had maintained throughout aircraft industry development. American workers achieved technical competence through standardized instruction that emphasized consistent results over individual artistic expression that Japanese tradition had valued in precision manufacturing operations. The research and development programs that supported continuous improvement in B-17 defensive capabilities operated without resource constraints that had limited Japanese aviation innovation throughout wartime equipment development. American engineers achieved systematic advancement in defensive effectiveness while maintaining production schedules that Japanese research organizations had never attempted during active military campaigns requiring immediate equipment delivery to combat units. International cooperation through B-17 operations provided American defensive technology to Allied forces while maintaining technological superiority that ensured continued leadership in strategic bombing capabilities. British, Soviet, and other Allied nations received American aircraft that enhanced collective offensive capability without compromising American advantages through strategic sharing that Japanese alliance systems had never achieved through coercive cooperation methods. Personal and collective transformation. The psychological transformation experienced by Japanese aviation professionals reflected comprehensive reassessment of American organizational superiority that had achieved military effectiveness through systematic methods rather than individual heroism or cultural discipline that Japanese military tradition had emphasized throughout national defense development. Captain Hayashi's analysis had revealed that former assumptions about American military capabilities were fundamentally incorrect across multiple critical parameters that would determine Pacific War outcomes. Squadron commanders throughout Japanese fighter units began acknowledging that their tactical expertise was being applied against defensive systems that rendered traditional Japanese advantages in pilot training, aircraft performance, and combat experience statistically insignificant compared to systematic American superiority achieved through industrial organization rather than military tradition. The mathematical realities documented in intelligence reports indicated that continued bomber interception missions would achieve insufficient success rates to prevent Allied strategic bombing while consuming Japanese pilot resources at unsustainable rates. Technical superiority demonstrated by American defensive armament reflected research and development programs that operated with resource availability and organizational efficiency that Japanese military industry had never possessed during peacetime development periods. Democratic competitive markets had encouraged systematic innovation that exceeded centralized planning achievements despite ideological motivation and administrative control that Japanese systems had maintained throughout military equipment development periods. The workforce diversity that contributed to American success challenged Japanese assumptions about social organization and industrial capability requirements. Intelligence reports documented that women, minorities, and immigrant workers had enhanced rather than compromised manufacturing effectiveness through systematic inclusion that democratic society had enabled despite traditional limitations that authoritarian systems had imposed on technical participation in precision manufacturing operations. Personal reconciliation between former strategic assumptions and mathematical realities occurred through shared understanding among Japanese military professionals that individual excellence could not overcome systematic industrial advantages that democratic organization had achieved through competitive innovation, inclusive participation, and systematic manufacturing that would reshape global military relationships for generations following Pacific War conclusion. Economic and technological revolution. Economic analysis of American B-17 production revealed cost efficiency that achieved superior defensive performance while maintaining lower per-unit manufacturing expenses through systematic optimization that mass production had enabled. Democratic capitalism had demonstrated economic advantages that exceeded command economy organization despite administrative control and ideological conformity that Japanese industrial planning had emphasized throughout wartime mobilization efforts. The innovation acceleration achieved under American mass production conditions contradicted Japanese assumptions about the relationship between quantity emphasis and technological development capabilities. American engineers had accomplished systematic improvements through competitive methods that centralized planning had never achieved despite bureaucratic efficiency and cultural discipline that Japanese research organization had maintained throughout military technology advancement programs. Manufacturing quality achieved through American production methods exceeded Japanese peacetime specifications while enabling systematic output volumes that traditional craftsmanship had considered impossible without compromising functional performance requirements. Statistical quality control had solved fundamental manufacturing problems through systematic approaches that individual expertise had never adequately addressed in Japanese precision manufacturing traditions. Supply chain coordination supporting B-17 defensive armament operated across continental distances without transportation disruptions that had consistently plagued Japanese manufacturing since Allied interdiction campaigns began targeting logistics networks throughout Pacific territories. Components manufactured in multiple locations arrived on coordinated schedules for final assembly while maintaining delivery timing regardless of strategic bombing campaigns that had systematically disrupted Japanese industrial operations. Strategic planning and future implications. Strategic implications of American B-17 defensive capabilities extended beyond current military operations to encompass post-war global relationships that would be determined by industrial capacity rather than military victories achieved through individual courage or tactical innovation that Japanese military culture had emphasized throughout national defense development. American defensive technology represented systematic advantages that would influence international security relationships for decades following Pacific War conclusion through industrial mathematics rather than battlefield determination. The preservation of American aircraft production capacity would define post-war global aviation through technological leadership that extended beyond military applications to encompass civilian transportation, commercial aviation, and international cooperation programs. Democratic Industrial Organization had created capabilities that would reshape global relationships through productive efficiency rather than military dominance that authoritarian systems had attempted to achieve through coercive methods. Innovation continuation beyond military requirements included civilian applications of defensive technology that would dominate post-war global markets in precision manufacturing, mechanical engineering, and systematic quality control. American engineering had created systematic advantages that would influence international industrial competition through competitive excellence rather than military superiority that Japanese strategic planning had assumed would determine technological leadership.
British international cooperation through aircraft sharing had demonstrated American ability to support global alliances while maintaining technological superiority that ensured continued advantages in aviation development. Democratic values had created sustainable partnerships based on mutual benefit, rather than coercive relationships that authoritarian alliance systems had imposed through military force and ideological conformity. The mathematical certainty of strategic reality. The final statistical analysis compiled by Captain Hayashi's intelligence team reached Emperor Hirohito and the Supreme War Council in December 1943, carrying comprehensive documentation that would eliminate every remaining Japanese illusion about the mathematical possibility of preventing Allied strategic bombing through conventional fighter interception tactics. The evidence was mathematically irrefutable and strategically overwhelming. American B-17 defensive capabilities had achieved systematic advantages that rendered Japanese resistance futile regardless of tactical innovation, pilot courage, or strategic resource allocation. The documented statistics revealed American manufacturing philosophy that treated defensive superiority as routine industrial achievement rather than maximum effort requiring exceptional national sacrifice or cultural dedication. Technical analysis confirmed that American defensive equipment exceeded Japanese military specifications while being produced in quantities that Japanese industry could never approach through any conceivable resource reallocation or manufacturing innovation. Democratic competitive organization had encouraged systematic advantages that traditional hierarchical methods could not replicate through cultural discipline or ideological motivation that Japanese systems had maintained throughout national development. The workforce development that enabled American success provided lessons for Japanese industrial recovery that would influence post-war technological advancement and democratic transition. Systematic training, educational opportunities, and social mobility had created human capital advantages that would define international competition for generations following military defeat through industrial capability rather than military occupation. Personal transformation among Japanese military leadership reflected complete reassessment of American capabilities that extended beyond defensive armament to encompass social organization, economic systems, and cultural values that enabled systematic advantages through democratic participation rather than hierarchical control that Japanese tradition had emphasized throughout national development. Conclusion: the legacy of mathematical reality. August 15, 1945. Emperor Hirohito's surrender announcement reached Japanese military headquarters as Captain Hayashi contemplated intelligence reports documenting American B-17 defensive capabilities that had rendered Japanese bomber interception mathematically impossible rather than merely strategically challenging. The final statistics were overwhelming and historically decisive.
American defensive armament had exceeded Japanese fighter capabilities by mathematical factors that made individual Japanese pilots' skill statistically irrelevant to strategic outcomes determined by industrial capacity rather than military virtue. Democratic abundance had achieved systematic advantages that authoritarian sacrifice could not overcome through ideological dedication or cultural conformity. The guns that couldn't be believed had represented more than defensive weapons. They had demonstrated systematic advantages that democratic societies possessed through competitive innovation, inclusive participation, and industrial organization that would reshape global relationships for generations following victory achieved through manufacturing mathematics rather than battlefield heroics. If this incredible story of how American defensive engineering overwhelmed even the most sophisticated enemy fighter tactics inspired you, make sure to subscribe to our channel for more amazing tales of how democratic innovation changed the equations of aerial warfare forever.